Recording. Great. Terrific. Okay. So this morning, I'm going to go over the t-test. Basically, what you can expect for tomorrow is going to be some short answers, maybe some very brief calculation or something like that, but things you can answer like with a number or by checking off a multiple choice or something like that. And then three SPSS problems. One is going to be t-test, one is going to be chi-square, and one is probably going to be analysis of variance. Although the analysis of variance, I may just show you a table or something like that and ask you to tell me something about it. So I may not, rather than like really pressure for time, I may give you something a little bit simpler on that. So I'm going to start by taking a look at the t-test. So our objective today is get the t-test, really understand that, and be ready for the exam tomorrow. Okay, so let's take a look at the homework. On the homework, our first problem was a t-test problem. I actually announced it. On the test, you might have to, recognize the fact that it's asking for two means. Might not say at the top t-test. You might have to make a little bit of an assumption about that or figure it out. Okay, so first thing that they ask you to do is open the uh, 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 open the file in SPSS. I started SPSS already, um, so that we wouldn't have to wait for that ball to bounce up and down. But if you have yours available somewhere soon, you might want to do this with me. So we're going to, the homework used the North Carolina birth date. I'm going to open that here. Okay, so I got it on my desktop. You navigate to it wherever you manage to put it. And I think it's in here. And sure enough, here it is. Okay, here we go. It happened to open up in the variable view. That's not a big deal for us. It's all already coded. Okay, it's labeled sensibly. It's coded sensibly. Some of the data files used for your project, you actually have to go in here. For instance, gender. You might actually have to go in there yourself and put in male and female. And you might actually go into the label field and where it says, where it had a complicated question, which was the question from the survey, you might actually have to go in there and, change it to something like just age of the mother or marital status, just so it simplifies it when you're creating graphs and so on and so forth. Okay, so I'm going to go back to the data view just because I feel a little bit more comfortable. Everything I'm doing will work in either view, but I'm going to go to the data field just simply because I feel more comfortable working that way. I'm going to minimize the output window for now. So let's take a look at what they ask us to do. Your variables are marital status and T ounces, birth weight in ounces. So let's take a look at that. Our variables are marital status, M status. Well, where is M status? Let's see if I can find it here. Well, let's see. It's actually marital is the name of the variable. If you take a look at this, the name of the variable is marital. The label is marital status. And the other one, the other variable that we're going to be working with was, get back to my Word document. The other variable that we're working with is T ounces or birth weight in ounces. Let's see where that is. So it's marital and T ounces. Okay, the birth weight of the child in ounces at birth. Okay, now notice that marital status is a nominal variable, and T ounces, or total ounces, or weight of the child in ounces, is a scalar or numerical variable. Okay, so that means marital status happens to have only two values. It could have had more, right? It could have married, not married, separated, divorced, so on and so forth, right? But it just had married and not married. Okay, so it only has two values. So we know that if we want to compare married women to unmarried women in terms of the birth weight of the babies, which is a numerical variable, we're going to use a t-test because it's a categorical variable with only two values. In this case, married, not married. It could have been male and female. It could have been old and young. It could have been anything with just two values. And a numerical variable, the weight of the child in ounces. There's also weight of the child in grams. In this case, I just randomly chose ounces for our purposes. Okay, So let's go here and let's go ahead and see what we have to do to complete this analysis. I'm going to go to Dave View. Let's go back to the Word document and see if it's asking us to do anything else. The first thing it's asking us to do is provide a null and alternative hypothesis. Okay, alpha equals 0.05. It's assigned us a maximum error of 5%. So we want to decide whether there's a difference between the two means of these two populations, but we don't want to accept any more than 5% chance of being wrong. So we have to provide a null and alternative hypothesis. So in our case, it's going to be mu is equal to the mu of married women. Mean weight for married women is equal to mean weight for unmarried women. Okay. Our alternative hypothesis. Let's put that in front of there. Our alternative hypothesis. Well, that we can get into a little bit of a discussion about that. Our alternative hypothesis is going to be that unmarried women, the weight rather for unmarried women. Actually, I'm going to put that in there. Birth weight for unmarried women and birth weight for married and unmarried women. Birth weight is equal to is not equal to rather the birth weight, mean birth weight for unmarried women. Okay, now first of all, what kind of null and alternative hypothesis is this? This is a two-sided hypothesis. In other words, if we look at the unmarried women and we're wondering whether the married women's weights are different than the married ones, well, that's two-sided because we haven't presupposed whether or not their birth weights are less than or greater than the married women. So we could have an outcome where we find that the unmarried women have larger babies, or we can have an outcome where unmarried women have lighter babies. So we haven't presupposed that. So all we're proving here, all we're demonstrating here, is that they're not equal, single-sided. Now, what would have made this, double-sided? What would have made this single-sided? Well, let's say that I already had a sneaking suspicion that in most populations that the birth weights for unmarried women is less than the birth weight for married women. Well, you might make that assumption. You might make the assumption that the birth weight for married women is greater than the birth weight for unmarried women. So you might make your null hypothesis may look like this. Our null hypothesis, that our belief that we want to reject, is that unmarried women, or if you wanted to prove that unmarried women were had birth weights that weighed more, actually, in the case that we're postulating here in this example. In this example, I'm saying unmarried women, I'm assuming, starting off, unmarried women have the same birth weights or greater married women have the same birth weight or greater birth weights than unmarried women. And what I might be proving, if I reject my null hypothesis, is in fact married women have lower birth weights than unmarried women. Okay, this one suggests that married women have greater or equal to, and in this one suggests that unmarried women are less than or equal to. I could postulate it the other way if I wanted to, but I would need some reason for doing that. In other words, I would have to have something that would some research that was done before, some physical effect, something that would tell me it could not be the other way. Otherwise, you would stick with the two-sided hypothesis. Okay, a one-sided hypothesis, because you're allowing all of the error to be in one direction. A one-sided hypothesis is much easier to prove than a two-sided hypothesis. It's much easier to reject the null hypothesis for a one-sided hypothesis. Okay, the other thing that you have about this is that okay, well, I just want to move on from that. We'll leave that as it is. Well, one other thing I wanted to mention is that the equality, right? The one that's always where the equal sign is, the equal or the equal and less than, whoops, the equal and less than, or the equal and greater than, the equal sign, the actual equal is always in the null hypothesis, never in the alternative hypothesis. Alternative hypothesis is always going to have either not equal to or less than or greater than. Okay, so I'll try and speak a little louder. In fact, I'll crank up the volume a little bit, I guess. Okay, that also might be on your end also. You might want to check your volume or whatever, because occasionally that does show up that way. Okay, let me crank it up a little further. Good. I'll try and face forward all the time. Not turn my face away. Okay, so let's take a look at the next one. What type of t-test is appropriate? Okay, you guys can tell me this. Is it, can we state it in a sense? For our purposes, I'll say yes. Obviously, if I give you a multiple choice, you're going to have to pick from the multiple choices. But I would say for our purposes, I would find that acceptable, that if you stated it correctly as a sentence, that would be okay. In some cases, it's even easier to do that. Like when we get to chi-square, and so like when we get to chi-square, for instance, it's somewhat easier to do that. Okay, and when we get to regression later on. So now, what type of test is this? Is this an independent, paired, or single sample? Any opinion? Yes, independent. It's not paired, right? Because paired would be if the women had two babies and we compared the two babies, for the same woman, right? In that case, that obviously that wouldn't be practical, right? So this is independent. Okay, so oops, looks like we did that again. Don't worry about that. We already did that. I thought I had taken that out when I revised it, but I guess I missed it. Okay, perform a t-test, alpha is equal to 0.05, using SPSS to compare birth weights by marital status and paste the results in the table below. So I'm going to go to SPSS, which I hope I've opened already. Yes, I have. Okay, so, and we looked at our two variables. And I'm going to say analyze. And so now we're comparing the means of two groups. So from analyze, I'm going to go to compare means. And since we already decided it was not a paired t-test, it's not a one sample t-test because it's two samples, right? The married women and the unmarried women. We know it's not analysis of variance because that involves three values. If we had married, unmarried, single, divorced, separated, so on and so forth, if that was the case, then we would use analysis of variance because we'd have more means than just the married and unmarried to compare. But in this case, it's independent samples, t-tests, of course. Okay, so now our test variable. In here, we put the numerical variable that we're going to find the mean of. A little confusing here because test variable, we have two of them, right? So which one should we put in there? It's not that obvious immediately. On the other hand, grouping variable is a little bit more obvious because when we look at grouping variable, we say, oh, maybe that's how we have to group the two means into married women and to unmarried women. So it's a little bit more obvious that that's the nominal or categorical variable goes into there. Okay, so I'm going to move in T ounces, or the weight of the child in ounces. You really can't. If you hover over this, I believe, yeah, if you hover over it with the pointer, it will actually expand so you can see which one it is. And the grouping variable is going to be marital status. So here we go for marital status. I'm going to click on that, and I'm going to move that into grouping variable. Well, before you can go any further, notice there's two question marks in here. You have to define the groups. Okay, so you click on that. Now, since the data is actually defined, is actually numbers that are labeled as married and that are labeled as married and unmarried, then you might notice, or it's handy to have this showing here, and I can see that actually, as far as SPSS is concerned, these are really ones and twos that we're analyzing. So I have to tell it that the group that we're comparing group one to group two. Why does it require you to do that? The reason why it requires you to do that is, let's say marital status had included married, unmarried, one and two, and then three was separated, and four was divorced, and so on and so forth. Well, then what you could have done to do a t-test is you could have gone here and said, use the specified values. And if you wanted to compare married to unmarried women, you'd put one and two in here. If you wanted to compare married to divorced, you'd put 1 and 3 in here. So you could still do a t-test if you're only interested in 2 groups, if there are actually more groups in that particular data set. Okay, so it's 1s and 2s. So I'm going to click OK. Well, we can click just so you see it. If you click into options, the only thing that it's by default, it's set at 95% confidence interval percentage. That's the same thing as saying do our analysis for 5% chance of being wrong. Okay, so I'm going to click OK, and it'll go ahead and do our analysis. Okay, so it comes up with 2 tables. The first table is a summary of our data, right? And meaning our descriptive statistic. And it says we have 537 women, married women in this study. We have a smaller number of unmarried women. We have a mean of 119 versus a mean of 109. We see that married women tend to have larger babies than unmarried women for whatever reason that might be. Okay, a standard deviation is 20 and 24. Those are actually not very far apart. If they get to the point where they're like one's more than double the other, then you start to think about maybe the variability, the standard deviations for the 2 groups are different. Okay, so and you might know that since we know how to calculate standard error, you might have already figured out that it calculated standard error by taking the standard deviation over the square root of the sample size right here. If you did that calculation with a calculator, it should come up about the same. So that's the data for each individual. That's the descriptive data for each individual group within marital status for the average birth weight. So now we could go ahead and we could do a t-test. In fact, we might do a very brief one shortly, right? So now I'm going to go down here to the next box, independent samples t-test. Okay, what happened in the independent samples t-test? Well, let's see. We have 2 separate areas here, right? We have one area here where we have these 4 boxes. You can kind of see they're separated. There's a line here that separates the Levene's test for the equality of variances from the t-test for the equality of means. So the t-test is under this area here. The test for the equality of the variances is here. These are not really the same table. They summarize it into the same table. So let's take a look at this. First thing SPSS does, it tests for the equality of the variance. Now I said, the variance, the standard deviation here, standard deviation and variance are really kind of two sides of the same coin. The standard deviation is just the square root of the variance, basically, right? So we're talking about the same thing when we talk about the standard deviation and variance. Okay, so up here we looked at the standard deviation and we said, well, gee whiz, the difference is not that great, right? There's always going to be some difference, but it's not like one's double the other or more than double the other. So they're not that different, right? So we made a quick judgment, that most likely that the standard deviation is the same for these 2 groups. They're equal. The variance or standard deviation are equal. And we know, I'm going to show you some formulas later on. We know that there's a certain way that we would do our calculations in that case. Okay, so I'm going to go down here to our table and see how SPSS interpreted that. And if I take a look down here, I see that SPSS calculated statistics called F. Now that's not the same as our analysis of variance. When we go later on and we do analysis of variance, we calculate an F. Don't assume that that's the same deal there. Okay, so calculated this test for quality of variances, and it came up with a value of 1.64 and a significance, a p-value, a probability of being wrong if we reject a null hypothesis. That's our significance or p-value of 20%. 20% we'd be wrong if we rejected the null hypothesis. Well, what null hypothesis is it talking about? The null hypothesis that it's talking about is that the variances are equal. The alternative hypothesis that it's talking about is that the variances are not equal. Okay, so if I look over here, it tells me I have 20% chance of being wrong if I reject this assumption that the variances are equal. That's unacceptable to us. We only like small chances of being wrong, like 5% and less, right? So basically we fail to reject our null hypothesis. That means we're stuck with equal variance is assumed, rather than stuck with where it's suggested that we'll use that analysis. In fact, SPSS will look at the formulas. There's two sets of formulas that you use for calculating the t-value. One formula you calculate the t-value using when you assume that the variance is equal. The other formulas are used for when the variances are unequal. In this case, our assumption is that they're equal. We don't have enough evidence. This is not less than 0.05, so we can't reject the idea that they're equal. So we're going to use the top line. We're going to ignore the bottom line, which would be the calculations for unequal variances, and we're going to use the top line. So SPSS has calculated these values for us. Okay, first thing it calculated was the degrees of freedom, right? Degrees of freedom, 798. Well, that's not such a surprise because it happens that there's 800 people in here, right? There's two groups, 800 people. We know where equal variance is assumed that the degrees of freedom is equal to N1 plus N2, that's 800, minus 2, one for each group. So it's 798. Now, look what would have happened. You might remember that there's a very complicated formula for calculating degrees of freedom when you assume unequal variances. And in fact, you get a very odd number for unequal variances assumed. Now, you might notice that this number is between the somewhere between these two groups, 263 and 537, right? So the bigger this number is, the better off you are, because the degrees of freedom is one of the things that helps you get a low critical t-value. So you want that to be a big number. Well, if you don't want to spend a lot of time calculating this number by hand, a lot of times what the researchers will do on preliminary analysis, since they know this number is going to be between 263 and 537, the two sample sizes, they'll just take the smaller sample size and use that temporarily, at least until they can get to SPSS or a program or something like that to do the calculations. That's a quick way of avoiding that really nasty calculation. So I'm going to go over here and I'm going to say, okay, what is the t-score? What is it calculated? Well, it took the difference between the two means, 119 minus 109, again, you can see this in the formulas, and divided that difference by the standard error. And how did it calculate the standard error? It took the standard deviation it calculated by pooling these two standard deviations, right, and divided by the square root of the sample size, and the standard error turned out to be this number, right, which was 1.62. But actually, what it did, it does something a little bit different than that. It actually calculates the mean difference between the two, and then corrects the standard error to be based on the mean difference. So if the significance was less than 0.05, we use the bottom line. Absolutely right, Leah. Right? That's correct. Okay, so basically it's taking the difference between the two and it's analyzing the difference between the two rather than the actual numbers in this description. But you don't have to worry about that. In any case, divided by the standard error divided by the square root of n, you'll get the same result. And the t-score, that number t is equal to x bar 1 minus x bar 2 over the standard error. A standard deviation rather, divided square root of n or standard error. That result is 5.848. That's what would be calculated as the t-score. Well, we know immediately that for a very large sample, that the t-critical is going to be very close to 1.96, right? So we know that if you get a value like 5, you know that your probability of being wrong if you reject the null hypothesis is really far below 0.05, right? But SPSS actually calculates it out. If we were doing this without SPSS, we might go to the table and check t against our t critical and see that our t has well exceeded our t critical, so we can reject our null hypothesis. In SPSS, we actually get a probability that we can compare to alpha, p-value compare to alpha, to decide whether to reject the null hypothesis. And in fact, the p-value is less than 0.001. It shows 000, but it could be 0.000297 or something like that. They round it to 0.000, okay, for our purposes. So we can reject the null hypothesis. So let's go back to what they asked us to do. And I know for sure one of the things they're going to ask us to do is to give us these results. Okay, I'm going to perform a t-test, compare the birth weights, paste the table or results in here. Okay, so those of you that have Macintoshes and that are using the same version of SPSS as I am are going to see how I deal with a certain problem that may come up right now that you guys have experienced. There's a very big table here. I'm going to click on that and I'm going to say copy. Okay, and I'm going to click back here and my cursor is in here. I'm going to say paste special. Now, I would like to paste this in as a picture because since it's such a big chart, I might want to resize it so it fits in here easily, or I might want to move it around. It's always easier to move around a picture than it is to move around or resize a chart with columns and tabs and so on and so forth, but it doesn't give me that option. Most of you, I would say 80% of you, are going to have that option and you'll be able to paste it in. The rest of you are going to be stuck with these, and you're most likely going to wind up pasting it in as a formatted text. And you can see what happened. Weight is a, in the married is a, yes, absolutely, Neil. Yep, that's correct. Okay, so I've pasted this in. Now you'll notice that in order to read, these are all different blocks. It's not that easy to select this and resize it. It would be much nicer to have this in here as a single block. Now, as a picture, an image, so that you can resize it easily. I'm going to show you how to do that in Macintosh. If you have that problem, and I think about 20% of you might actually have that problem. Now, if you, for the purpose of the exam, if you have any problem with paste special and you don't find the image in there and stuff, if you paste it in this way, it'll be acceptable. I'm not going to expect you to make up for the shortcomings of the software or bugs in the software. Okay, so I'm going to undo this and show you how I would do it on my computer, which has this problem. Now, on the Macintosh, I'm going to click in the background, so I'm in the Finder. If you look up here, you guys that have Macs will know that if you're in the Finder, you see Finder file. There's one thing called Go here. I'm going to go to Go, and I'm going to go to Applications. Whoops, I didn't mean to do that. Go and Utilities. Okay, and it's going to list a whole bunch of utility programs. One of the utility programs is listed is something called Grab. Okay, so now I'm going to double click this. Now, if you want to keep it handy, you can just click and grab this, literally grab, I guess, right? And you can grab it down to your menu bar down here, your start bar down here, and then leave it down there, and actually it'll connect, and it'll be there for you to use in the future. So you don't have to go back to utilities and use it. In fact, I'll do it that way right now. Okay, I'm going to click that, and it starts that up. Starts up that program called Grab. Actually, I should have gone back to SPSS first. I'll do that now. Okay, so here's the table that we want to copy. Right, here's our table. Yeah, okay, good. Did you figure it out? Oh, good, excellent. I'm glad that at least, yeah, good. A little tricky, right? Okay, but it works very well. So I'm going to go here. I'm going to click Grab. Now, Grab, the menu at the top changes, and I'm going to select Capture, Selection, so that I can select what I want. I can just go right over this box. It'll create a copy, an image of what's on the screen that you selected. So here's my table. Now, I can either say Save, right? Give it a name, drop it on the desktop, drag it into my Word file, or insert it into my Word file using the insert command. I could either do that, or I can, if I'm not interested in saving the picture, I can even just say copy here, and it will copy this picture. So now I don't need it anymore, and I can tell it don't save it, go back to my Word document, and I would actually paste it in before you sent it away, before you closed and didn't save your SPSS file, just to make sure it works. And then I'm going to say, well, you can say paste special, but the only option is going to be a picture because that's what this is a picture. I'm just going to say paste. And now you have it in there as an image. Right now, obviously, the numbers look a little smaller because you've condensed it, but you can make it larger. You can make it even smaller. It's easy to pick up and move to another spot, and so on and so forth. So a lot of you may find that that's a lot easier to do than to try and struggle with that bug that's in SPSS where it doesn't put an image into the clipboard. Okay, so does SPSS indicate you should consider the variances of to be equal or unequal? Okay, so what do we say on that? We said, let's assume that the variances are equal, right? It didn't give you enough evidence. It said you didn't have enough evidence to say that they were unequal. Okay, and what is the value of your T analysis? Okay, T-score was, I think, 5 point something. I'm just going to put 5 for our purposes. What was the p-value of your significance? And you could either just say point 0.000. What might be a little bit more accurate is less than 0.001, because it's smaller than that rounded number of 0.000. So either one of those is fine. And what is your conclusions regarding your null hypothesis? Anybody want to hazard a guess as to what your conclusion should be, properly phrased, for your null hypothesis? What do? What do we do with the null hypothesis? We reject the null hypothesis. And what do we do with the alternative hypothesis? Accept. Good. Okay. So what we've just proved, or proved at least to a certain level of probability of 5%, that the birth weights for single women in North Carolina during this period of time, that population, that their birth weights with at least 95% certainty or less than 5% chance of being wrong, we've proved that the birth weights for single women were lower on average than they were for married women. We use a two-tailed signature to evaluate the hypothesis. I wouldn't worry about that. It's probably a single-tailed test, actually. But if you had needed to use a two-tailed significance, and you may notice that in the box on SPSS, that it actually performs a two-tailed test. In other words, its p-value is for two-tailed, right? Which is double, which is half the value, half the likelihood, but double the area. It's a little complicated concept just looking at it here without showing you the normal distribution. But it always does a two-tailed test. It never does a one-tailed test for a T, unless you do some special manipulation. Right? It does a two-tailed test because in most cases you're going to be using a two-tailed test anyway. It's a more conservative approach. On significance, to be honest with you, I'm not sure why it doesn't show it as a two-tailed test. It may actually be a one-tailed test, kind of like chi-square is or something like that. But I wouldn't worry for our purposes. I wouldn't worry about that. But we can actually look it up. I mean, if you wanted to go a little further, and we had a little time on our hands, we could actually look up how Levene's test for quality of variances performed and why they don't show in SPSS. The result is a one-tailed or a two-tailed test, just shows the significance. It even shows two-tailed when you do a calculation for chi-square, even though we know that looking at the distribution for chi-square, that's basically always a one-tailed test. So that's where we stand there. Now, just to show you the formulas, I put up a reference block. Oops. I'm going to say no to this. Okay. And I put up a reference block on Blackboard. There's a little tab on the left-hand side called references. Okay, and in that reference block, let me get rid of this so I don't forget. Do a little housekeeping. In that reference block, I put formulas and tables that might be handy to you. Okay, one of them is the procedures for doing a t-test. Okay, and here proportions, sample size of 30, at least 15 in each outcome. Oops, that got ahead of myself there. Here is how to do a t-test, assuming that standard deviations are assumed to be equal. Okay, and usually I would assume them to be roughly equal. If, by the way, just so you know, when the assumptions that SPSS makes when it does a a t-test with unequal variances, it assumes that the sample sizes are roughly equal. That could be a very bad assumption. So there's certain things that if you're a professional statistician, that you understand about the way SPSS does things, that you, when you take a look at that table, are going to make may make some corrections to the way SPSS, the technique that SPS uses. There's kind of a trade-off. We're not going to worry about it, but if you wind up doing the calculation at SPSS with unequal variances, if then the sample sizes have to be the same. If the sample sizes are different, are very different, like one sample size is twice the size of the other, and you try to use that test for unequal variances, it gives you a incorrect value for the significance, gives you a less conservative value for the significance. So you got to be a little bit careful with that. We're not going to worry about that. A real professional statistician would understand why that happens and how we would correct for that. I think there's a video online that I can probably link you to if you're really interested in why that might happen. Okay, so at any rate, okay, state your null hypothesis, determine your level of confidence, which is usually 0.05. Now, if you have standard variance with equal standard deviations, you would create a pooled standard deviation. Samples N1 is sample size of one group, N2 sample size of the other group. S1 squared is the standard deviation of one group squared. The other one is the standard deviation of the second group squared over N1 plus N2 is equal to this. So that's the way you would calculate a pooled standard deviation, not your standard error, pooled standard deviation for the two groups. And you can pool it because you're assuming that the populations really have the same standard deviation. Why not take advantage of all that extra information to calculate your more accurate standard deviation or standard deviation pool? And then when you do your calculation for t, you calculate t as the difference between the two means of the two groups divided by the standard deviation pooled over the square root of the sample size. However, since you're using two different sample sizes, you're actually multiplying the pooled standard deviation by the square root of 1 over n1 plus 1 over n2. It's the way that you make up for the fact that it's a larger sample size as well, right? So a little bit different calculation, but you come up with a t-test, a t-value. Your degrees of freedom, and we saw this already, is equal to n1 plus n2 minus 2. So you calculate that. Okay, in our case it was 800, was the sum, and minus two groups is 798. And we compared the critical value of t, and we got 5. If you compared it to t, t was 1 point, probably for that size 1.97 or something like that. So in our case, basically 1.96. So we could then reject the null hypothesis without using anything other than our calculator, our quick wit, and and the accessibility of a t-table if we needed it. And in fact, we probably wouldn't need a t-table because since the sample size is so big, we could just use our knowledge of 1.96 being the z-score for very large samples. Okay, and we can decide to reject or accept. Difference that we have with comparing the means of two populations when you don't assume the variances are equal. For instance, if you saw that the standard deviation of one group was one sample was 22, and the standard deviation of the other sample was 6, that's more than a double difference. It's a very large difference. Well, in that case, the way you would calculate the t-score is that you wouldn't pool the standard deviations. You'd do a slightly different technique. You'd use x bar 1 minus x bar 2, normal calculation, divided by the square root of the standard deviation of the first group squared over its sample size, plus the second group squared over its sample size, then add them together and then find the square root of everything. That would represent your standard error, difference in the means divided by standard error. A kind of a simpler calculation than we did up there for equal variances because we didn't have to pool them, right? But the trade-off is look how complicated the formula for degrees of freedom is. And as I mentioned before, rather than doing this calculation, especially if you have a really big sample and it's not going to affect the t-score, critical t-score that much, instead of doing this calculation, you might just take the smaller sample and subtract 1 from that and use that as the degrees of freedom rather than go through the torture of calculating. I actually said that there. Okay, now finally there's proportions. The way proportions work is you got to do the same deal here. You have two proportions, like for instance, if you had one proportion was 30 out of 100 people, and the other proportion was 20 out of 100 people, and you wanted to know if you could say with less than 5% chance that the proportion for the populations they came from are really different, well, 30 over 100 people is 0.3, 20 over 100 people is 0.2. So you would put 0.3 minus 0.2 to calculate your z-score. Again, we only do that if we have enough people use a z-score, 15 in each group, right, and 30 total minimum, right? So we have 0.3 minus 0.2. Now, our standard error on the bottom gets a little complicated, right? And what we have to do there is we have to calculate a pooled proportion for that, okay? So we're not going to use, notice it says PCAP and PCAP here, right? But it says PCAP 1 and PCAP 2 for the two proportions, 0.3 and 0.2. Down here, it doesn't have a 1 or a 2. That's because you use a pooled proportion. That's calculated up here. And how do you calculate that? Well, they do it a little complicated. Proportion 1 times the sample size, proportion 2 times the sample size over the sum of the two sample sizes. If you remember, it was 50 over 100. 30 over 100 was one group. 20 over 100 is the other group. So if I pool the two of them, the two groups are 50 over 200, the average proportion, which is 0.25. So this pooled P down here would be 0.25, and 1 minus 0.25, 0.75. And the sample size is pretty obvious. So that's what they mean. And this is a mathematical way of doing it. This would come out the same way as the description I just gave you. Okay, the point, 0.3 times 100 is 30, 0.2 times is 20, 0.2 times 100 is 20. That's 50 total over the sum of the two groups, which is 200. So it comes out the same way, same deal, right? And then you just calculate. Then you compare that z-score to to the normal distribution. So that would be the critical value of z would be 1.96. So if your calculation for z is bigger than 1.96, you can reject the null hypothesis. They're more than two standard deviations apart. If you want to calculate a p-value, you could actually take your z-score and go to your normal distribution table and actually calculate a probability of being wrong, a significance or a p-value of your own for that calculation. So, and you would know that, oh, now it's really 4% or 1% chance of being wrong, or even the 0.000 if it's really really low, like we got before. Okay, but you would look that up on the table. So that's the way you would calculate your z. You know that if this z comes out to be more than 1.96, your significance is always going to be less than 0.05 because it's going to be more than two standard deviations apart. Okay, so I think tonight we're going to go over the problems that we had in the homework. And like I said, you can anticipate that there'll be, in one form or another, an SPSS question about t-test, analysis of variance, and chi-square. Tonight we're going to go over, and then some short answers and stuff like that. Tonight we're going to go over analysis of variance and chi-square. Okay, so you guys can be as prepared as possible for tomorrow. Okay, so if you can make it, I'm going to try and get this up, posted as soon as possible. No, there's actually, if you go to the assignment section, there's a place now where you can click on and you can upload a file to the Blackboard. Right under the assignments tab, assignments 5, you'll see there an assignment where if you click on it, you can say browse and upload the file. Okay, but get some practice with SPSS, cutting and pasting into Word, because you don't want to be stumbling tomorrow night if you get into a little bit of time pressure. You don't want to have to like try and figure out how to put stuff into a Word document and then upload it to a question on the exam or browse for it and get to it and so on. So get a little bit of practice on that so you feel comfortable with it if you can. Okay, so have a good rest of the day today. And some of you, I guess I'll see you tonight if you make it back again tonight. Okay, but I'll try and post these things as quickly as possible. Take care, guys. Bye. Good morning.